Okay, so not on yet. Um, I so I was careful to get that assignment done and posted on the D2L news and everything before I left for the break. Like, okay, done with that, and then I didn't post the problems. They were just sitting there on my hard drive. So that's mainly just going to be the problem for the assignment for Tuesday. You know, it's up there now. So I'll probably assign it. I don't know. Maybe I'll just make it that since it's only 2-day assignment, and then I'll give you some new stuff on Thursday. Does anyone have any questions about homework? Okay, those are the best kind because everybody's embarrassed to ask about it. Oh, okay. 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 Hmm. Yeah, okay. Okay, so this is an ideal gas thing. Number 4. Show that for an ideal gas, CP over CV is 5/3. And then how does that compare for an incompressible material? Well, for an incompressible material, they're the same. So that's how it compares. That ratio would be 1 for an incompressible material. Okay, so for this one, so what do we have? CP is equal to the partial of the enthalpy with respect to temperature holding pressure constant. Is that right? CP. Yeah. And CV is du dt holding volume constant. H is equal to internal energy plus P specific volume. And we know that it's an ideal gas, so we know that PV is equal to RT, where this R is specific to the gas. That's not the universal one. Okay, so U okay, so let's think of so dH dt is equal to partial with respect to temperature of U plus PV this is for pressure constant. Okay, and from the ideal gas law, PV is equal to RT, so we can write that as partial with respect to temperature of U plus RT, holding pressure constant. And that's equal to partial of U with respect to temperature for P constant plus R. For the ideal gas model, do we have the assumption is, I think, that the internal energy is only a function of temperature. Is that right? Can someone look? I don't know if I have that with me here. Just when I list out the assumptions for an ideal gas. Yeah, internal energy is a function of temperature. Okay, so okay, so here are the assumptions for okay, here are the ideal gas assumptions. So first, PV equals RT. Second, internal energy, specific internal energy, is just a function of temperature. And third, H can be approximated, bless you, as internal energy, which is a function of temperature, plus RT. Okay, well, that was sort of what we were getting at there. Well, using the fact that U is just a function of temperature, then we don't have to worry about holding pressure, excuse me, holding pressure constant versus holding volume constant. Those, it's not functions of those. Okay, so this tells us that Cp is just equal to the total derivative of H with respect to temperature. This is a restart, by the way. I don't know if you could tell that. These are notes to self. Only. Okay. So Cp is this, and Cv is the total derivative of U with respect to temperature. This is the total derivative with respect to temperature of H is equal to U plus RT. So take that derivative and you get du d temperature plus R. And we're looking for Cp over Cv. So we have du d temperature plus R divided by du d temperature, and that gives us 1 plus R over du dt is CV. Let's see, so we got this, and that's also equal to this. Okay, so we want to figure out that R over CV, or R over du dt, is equal to 2/5. Anybody remember how to do this? So let's see. R is equal to PV over T. So we have 1 plus PV over T du dt. But it definitely did say that for an incompressible material, a liquid or a solid that you're treating as incompressible, CP is just equal to CV, and we just call it the specific heat. All right. So what we've been talking about is control volume stuff. First law of thermodynamics for control volumes. The full general equation says the change in the energy of a material in the control volume is equal to the rate that heat enters the control volume minus the work done on the surroundings by the control volume plus the rate of mass flow through the inlet times the quantity enthalpy at the inlet plus speed squared over 2 at the inlet plus G times height at the inlet, and then minus rate of mass flow the exit times the quantity H exit plus speed at the exit squared over 2 plus GZ at the exit. And then depending on what kind of device control volume you're looking at, you eliminate some of these. So the first thing we talked about was nozzles and diffusers. Where a nozzle speeds up the flow and decreases the pressure. So that's low V and high pressure. And over here, you know, it's going this way. Over here it has high V and low pressure. And a diffuser is the opposite. At the inlet, you have high speed and low pressure. At the outlet, you have low speed and high pressure. And the simplified form for that one said, you can write it a couple of ways. Zero is equal to the enthalpy at position 1, or let's call that the inlet, minus the enthalpy at the exit, plus the speed at the inlet squared over 2, minus the speed at the exit squared over 2. Okay, so you can think of nozzles and diffusers as exchanging enthalpy for speed and pressure. So the next one, we did an example, I think, last time with that. The next one is turbines. And in a turbine, a fluid, a gas or a liquid, hits blades to rotate a shaft, and that produces power. You could use it to do physical work, or, you know, more often it's used to produce electrical work through, you know, you have a magnetic field and that rotating thing produces electricity. And the idea here is that you exchange enthalpy for electric power, or it could be mechanical power. So let's think about the simplifications here. Here's a sort of a drawing of what it might look like. So you have a shaft. In this case, we have 2 turbine blades. So here are the blades. These are inside a tunnel. This is a solid shaft. Okay, so all of this shaded region is solid. And you have a flow of steam or whatever material this way. And it leaves this way. And when that fluid hits these blades, it turns that shaft, and that's how the power is created. So here are the assumptions that we're usually going to make with turbines. First, there's no material stored in our control volume, so whatever the mass flow is coming in is the same as the mass flow going out. So in other words, the rate of mass flow at the inlet is equal to the rate of mass flow at the exit, and we'll just call that m dot. Second, steady state. So the rate of change of energy in the control volume is 0. Fluid, usually to turn these blades, it needs to move through the control volume pretty quickly. So we're usually going to assume that there's no heat transfer from the control volume to the surroundings. This one is a little surprising, but we're going to do an example that shows sort of in a typical case how this works. The kinetic energy contribution to the first law of thermodynamics is small. So S is treated as 0. It's just always going to be small compared to the other terms. And then also the change in height of the fluid is not going to contribute much to this. So we'll assume that m dot times the quantity gz at the inlet minus gz at the exit is equal to 0. And again, that's small compared to and so the first law with these assumptions says 0 is equal to negative of the work done on the surroundings by the control volume plus m dot times the quantity enthalpy at the inlet minus enthalpy at the exit. And you can rewrite it as the work done by the material in the control volume is equal to m dot enthalpy at the inlet minus enthalpy at the exit. Okay, so this is for a turbine. So that W dot is the work that is given away by the control volume through electric power. That's electric power that's created. Can I what? Yeah. Mm-hmm. Okay, so there is going to be a change in speed from one side to the other side normally. But that, so we'll see that in this example. But that change in speed just isn't going to be a very big source of change in energy. Okay, so let's say that this is a steam turbine. So that means that the material moving through the turbine is steam. The rate of mass flow is 4,600 kilograms per hour. At the inlet, we know that the pressure is equal to 60 bar. The temperature is 400 degrees Celsius. And the speed is equal to 10 meters per second. And then at the exit, the pressure is 0.1 bar. The speed is 30 meters per second. And the quality of the saturated steam liquid is 0.9. So it's almost all steam, but a little bit of it has condensed into a liquid. And we want to know first, using the turbine assumptions, what's the power generated? And second, now this is sort of a realistic amount of power that you'd actually get out of it. Let's say that we get true power generation of 1,000 kilowatts. What's the rate of energy added to the control volume by kinetic energy? And then last, with that same assumption, so assuming that true power generation is 1,000 kilowatts. What's the rate of heat loss? Okay, so for part A, we're going to go to that fully simplified form that we're going to use for turbines. And then for B and C, we're going to go back to a more complete first law of thermodynamics using some of those other. So there's some values that are given that we're not going to use in part A. And then we'll go back and use those in B and C to figure out, how much energy you could expect to lose in something like this for heat, how much you could expect to gain or lose through kinetic energy. Okay. What do you think about? So look at the properties at the inlet and the exit. There's a much higher pressure at the inlet than the exit. Do you think that's always the case, or is that just this turbine, or what do you think? We always need it because that difference in pressure is what gets the gas to move in the direction we want through the turbine. Okay, so for part A, we're going to use this equation that says the rate of work done by the control volume is equal to the mass flow rate times the enthalpy at the inlet minus the enthalpy at the exit. We can use the steam table. And it says that let's see. Okay, so we know that at P1 of 60 bar and temperature 1 of 400 degrees Celsius, specific enthalpy is 3,177.2 kilojoules per kilogram. And now for the second, at the exit, we have to use the information about the quality, so it's going to be a little more complicated. At this second pressure of 0.1 bar, okay, so first of all, it doesn't give the temperature. How do we get around the fact that this problem doesn't give the temperature? Or how do we know what to do there? No, the temperatures are different, but because it gave the quality, we know that it's saturated. So now we can go to so we're going to use a different table for this. Let me put that here. So for the saturated water table, we know that at a pressure of 0.1 bar, for it to be saturated, and that's, only in saturation do you talk about a percentage of liquid and a percentage of vapor. The temperature, well, I didn't write it down, but you could look up the temperature. The specific enthalpy of the liquid part, we call that H sub F, is 191.83 kilojoules per kilogram. And the specific enthalpy of the vapor part, the gas part, H sub G, is 2584.7 kilojoules per kilogram. So based on that, how do we figure out the enthalpy of the mixture that we have? Well, we have 90% gas, 10% liquid. So H2 is equal to 0.9 times 2584.7 plus the quality, or 1 minus the quality, so times the enthalpy for the liquid, 191.83. And I think that gives you 2345.4. M dot is 4,600 kilograms per hour. All of our units are in seconds, kilograms, joules. So 4,600 kilograms per hour is equal to 1.27 repeating kilograms per second. And so plug this now all into the first law, and you get that W dot for the control volume is equal to 1.27 repeating times the quantity 177.2 minus 2345.4. And so you get 1,062.9 kilowatts. Okay, so if there was perfect efficiency, you could transfer all of the change in enthalpy directly into electrical energy. That's how much energy you'd produce. We didn't use all the values that were given in this problem, so now we're going to go back, use some of those other values to come up with sort of typical heat loss, typical, the other thing, change in kinetic energy, typical energy loss due to change in kinetic energy, and we'll see how this estimate compares to a more realistic value. Okay. Questions about that one yet?
For the T2,
Mm-hmm.
did you find the value for that, or you just
I assumed that I had, and then it wasn't in my notes, but you could look that up.
Okay.
If you know it's in saturation, then the pressure is enough information to find the temperature and vice versa. Okay, so for part B now. So now we want to figure out the term m dot times the speed at the inlet squared over 2 minus the speed at the exit squared over 2. So let's figure that out. And we can do that just using, we're given information about the speeds. So using the fact that at the inlet speed 1 is 10 meters per second, and at the exit, 30 meters per second. So we know that the rate of mass flow is 1.27 repeating. That is in kilograms per second. And so m dot times v at the inlet squared over 2 minus v at the exit squared over 2 is equal to 1.27 repeating times 10 squared over 2 minus 30 squared over 2. And you get a value of about negative 1022.2. But that's in watts. Our other answer was in kilowatts. So this is equal to negative 1.02 kilowatts.
You got a 50 minus 400, 450. You got 400 inside. Did you get something that's about 500?
Let's see. So you get 450 minus 400. I probably forgot to divide by 2. Yeah, could you tell me what that? Thanks for noticing that. Okay, negative 508 watts, and so in kilowatts, that's negative 0.51 kilowatts. So, anyways, less than 0.1% of the estimate that we got in the first place. So that's why we're usually gonna, tiny fraction. So that's why we're usually gonna throw that away. And then for C, now we want to, at the same state, figure out what the heat loss would be. We were just calculating the contribution to the first law that comes from changes in kinetic energy. And so now we're going to go back to the first law. So now what we're trying to find for part C is how much heat is lost, how much energy is lost through heat. So basically, we made this assumption that no energy was lost through heat, no energy was lost through the kinetic energy changes, and now we're taking additional measurements, hypothetical measurements, but that are supposed to be sort of in the ballpark of something realistic, to figure out how reasonable these assumptions were. So the first law now becomes, if we're, yes? We haven't needed it yet, but now we're going to need it. So in part A, we assume no heat lost, assume no significant kinetic energy changes, and we calculated using those big assumptions what electrical power would be generated. And now we're saying don't throw those away, and based on some additional measurements, let's figure out the amount of energy that is lost through kinetic energy, the amount of energy that is lost through heat. Okay, so we calculated here that in part A, that power generation was 1,062. A more realistic amount of power generation for all of these properties would be 1,000. So you lose 2.9 kilowatts. So we're just going to plug all this stuff into the first law and calculate the different parts of it. So the first law now, so we still don't have any change in energy in the control volume. We are dealing with heat now. And now we're making the assumption that the electric power that's produced is 1,000. So we'll subtract a positive amount of work done on the surroundings. And then we have 1.27 repeating times h at the inlet plus speed at the inlet squared over 2. We're still throwing away the height change. And then minus 1.27 repeating times the h at the exit plus the speed at the exit squared over 2. So 0 is equal to Q dot in the control volume minus 1,000 plus, I'll rewrite this as 1.27 repeating times, now we still know those enthalpies from before, this, nothing's changed about any of the values that we used before. And then we have plus 1.27 repeating times the speed at the inlet squared over 2 minus the speed at the exit squared over 2. And now we can just plug in values. So 0 is equal to Q dot for the control volume minus 1,000. We calculated before that 1.27 times that difference in enthalpies is 1062.9. This is in kilowatts. And we calculated that this term, m dot times the quantity vi squared over 2 minus v exit squared over 2 is negative 0.51. And so Q for the control volume, Q dot, is equal to 1,000 minus 1062.9 plus 0.51. And what do you get for that? Something negative. Does it make sense that we would get a negative answer for Q dot? Yeah, because that Q or Q dot is positive if heat is being added from the surroundings to the control volume. Here we have heat being lost from the control volume to the surroundings, so that should be negative. Yeah, that's kilowatts. Thanks. Any questions about that? Okay, so now we're going to talk about two things together, sort of the same way we talked about nozzles and diffusers. So now we're going to talk about compressors and pumps. Compressors are when you're talking about gases. And what you're trying to do in a compressor is change the pressure. So you always want the pressure to be higher at the exit than it is at the inlet. And a pump is for and you want to, usually you're using pumps to change the height. I guess you could use it to change the pressure. And for these, for nozzles and diffusers, we came up with one final simplified equation that related enthalpy change to speed change. And for turbines, we came up with one simplified equation that related enthalpy change to electric energy, right? Change in like a power generation. For these, every time we use these, we're going to make some different assumptions. There are going to be some that are going to be the same always. So we're not going to come up with a single simplified equation. It's going to be sort of a case-by-case thing. So here are the things that we're going to often see. So for assumptions. First, it's almost always going to be in steady state. I think probably every problem we do, it's going to be in steady state. So the time derivative of the energy in the control volume is equal to 0. It's moving pretty quickly, so we're usually going to assume that there's no rate of heat transfer between the control volume and the surroundings. Because it's steady state, there's no mass stored inside the control volume. So the rate of mass flow at the inlet is equal to the rate of mass flow at the exit is equal to m dot. And now we get into some that are dependent on the application. For compressors, we can assume that the change in potential energy is small. So it is like m dot times the quantity g z at the inlet minus g z at the exit is equal to 0. With pumps, that's not always the case. And 5, for pumps, the change in temperature and the change in pressure are usually zero. And so that's not always true with compressors. So let me elaborate on this one a little. So if you have a pump, here's what the little pump that we use looks like. You got this thing, sucks up the water here, and then so here's the inlet, here's the exit, and you're trying to get this up to a different height, or you're trying to overcome friction to spray this water out of a hose somewhere far away. Okay, well, when it says for a pump, usually the change in pressure is going to be zero. That seems a little strange if you think about the inlet being here and the exit being here, because obviously you need to develop a high pressure in order to shoot this liquid all the way out there, up high or whatever. But if you think of that control volume as being everything from the start over here, so now think of this as the inlet, and that is the exit. Then right here you have atmospheric pressure. Right here you have atmospheric pressure. And so you're doing all these calculations, not at the really where the physical pump machinery starts, but where you're picking up the liquid and where you're dropping off the liquid. Any questions about that? Okay, so let's do a problem with a pump. So let's say water is drawn from a pond. Rate of 0.0138 repeating meters cubed per second. Okay, I got that crazy number because I think I converted or something. And we want this water to be lifted a height of 10 meters. So what's the power required? That's electric power. Assuming that there's no heat loss. Okay, well, what assumptions can we make? We're going to make, we're going to assume that it's steady state, so dE dt for the control volume is 0. We're going to assume that there's no heat loss. We're going to assume that the rate of mass flow is the same all the way through. And now what about a change in potential energy? That's one we almost always, I think always up until now we've thrown that out, but now we're talking about, remember, if we think of our exit at the end of the hose, that's 10 meters up in the air. And so that's going to be important in this one. So we're not going to make that assumption. We are going to assume that the temperature is constant. And we are going to assume that there's no change in pressure. So there is change in potential energy. We can't get rid of that one. More? The temperature is constant, so we're going to assume that the density is the same. So rho is constant, and we'll just call that 1,000 kilograms per cubic meter. M dot is equal to, so we have volume flow. The density of water is 1,000 kilograms per cubic meter. And if you multiply that by 0.0138 repeating meters cubed per second, you get that M dot is equal to 13.8 repeating kilograms per second. And then Z at the inlet, the height at the inlet, we'll call that zero height. And the height at the exit is 10 meters higher, so we'll call that positive 10 meters. So now the first law says 0 is equal to 0 minus W dot for the control volume plus M dot times the quantity enthalpy at the inlet plus G Z at the inlet, and then minus M dot times the quantity enthalpy at the exit plus G Z at the exit. And now we can fill some of this stuff in. So W dot for the control volume is equal to That height is a fake. Okay, so W dot for the control volume is equal to, I'll write it as, I'm just going to rewrite it, M dot times the quantity HI minus HE plus dot times the quantity GZI minus GZE. And so that's equal to 13.8 repeating times the enthalpy. Now, the enthalpy is, so specific enthalpy is internal energy plus PV. Since we're assuming that the temperature is constant, this goes away. Well, let me write it like this. That internal energy isn't zero, but the change in internal energy is zero. So because of the constant temperature, this goes away because, so why doesn't the specific volume change? Well, pressure is constant, right? The specific volume does, the specific volume change is zero because we're assuming this is incompressible. The density is constant. And so this goes away. And we're just left with, all I need to do is damn it. Okay, hold on. I can do this. New page. Okay, so W dot for the control volume is equal to 0 plus 13.8 repeating times 0 minus 98.1, and you get 1,361.63 watts. Negative. Does it make sense in this case that W dot would be negative? Yes. In the case of the turbine, we were using changes in energy due to the properties in that control volume to calculate the work that's being done on the surroundings. This is the surroundings putting energy into the pump so that we can change the potential energy of the liquid. Any questions? Okay, that's all. So I'll put up a new assignment, but it might add a small amount to the assignment from the long weekend that I didn't get to you.